Hello, folks. Okay, so let's start. I'm going to continue with derivative and integral. Today we are mostly going to think about integral questions. But I'm going to start where we finished the other day. We started to talk about Darbus Theorem, but we didn't prove it. So let's start from Darbus Theorem, and then we would continue with integral. Okay. So let me remind you, we have different kinds of discontinuity, right? So sometimes the discontinuity points, they look like this. Sometimes you have a function f, and it's discontinuous at a point like this, which means it has, well, say this is point C, it's the point of discontinuity. The function f has right limit at C, limit of f of x, when x goes to C from right, it exists. The limit of f of x when x goes to C from left exists. But these two things are not equal, right? That's one kind of discontinuity. Another type of discontinuity is something like this. It means the function has, at the point C, the function has right limit. The right limit exists at that point. The left limit also exists at that point. And these two limits are equal, but the reason the function is not continuous is that they are not equal to the value of the function at that point, right? This is another kind of discontinuity. Finally, sometimes the right limit doesn't exist and the left limit doesn't exist. For example, look at sine of 1 over x. It is discontinuous at 0. This point C, the point of discontinuity, is 0 here. And the function, you know, it kind of looks like this. It becomes like that here, and it continues like this. And it's not continuous at 0. It's discontinuous there. Okay. So we have different kinds of discontinuity, and so let's just erase these and draw them. So sometimes they look like this. Sometimes, let's call this one F. Sometimes they look like this. Let's call it G. Sometimes they look like this. They look, for example, sine of 1 over x. Okay. Now, the interesting thing is that we know every continuous function has intermediate value properties, right? So I would write it here. Every continuous function has intermediate value property. But sometimes even discontinuous functions have this problem, this property. Now look at the function here. Intermediate value property says for any interval a and b, if we look at such an interval, if we look at f of a and f of b, well, without loss of let's say f of a is less than f of b. The other case is similar. For any number we choose in this interval, intermediate value property says there exists a point x naught in the interval a to b, where f of x naught equals c. Now, of course, here, the first example doesn't have this property, right? If I choose A to be this number and B to be this number, this is going to be f of A, and this is going to be f of B. And here C is somewhere in between, but as you can see, there is nothing between A and B such that its f is equal C. So f doesn't have intermediate value property. What about the second one? Does G is not continuous too, but does it have intermediate value property? Think about that for a minute. And tell me, what do you think? Okay, Kyle says it doesn't take on the value as the whole. This is correct, but remember, if you want to say it doesn't have this specific property, you should tell me what is the explicit meaning of every object in this theorem. For example, you should tell me what is A, what is B, what is C, and why there is no x such that f of x is C. So Kyle, what is A in the second question? If you want to say G doesn't have intermediate value property, we should kind of define a point A, we should define a point B, and then we should look at the interval FA to FB. So what is A here? Anyone can answer the question. So if you want to show it doesn't, if you guess the answer is no, first you should tell me what is A, and then you should tell me what is B. Suppose this discontinuity point is C. Okay, I would tell you the answer. Let's take A to be this discontinuity point C. So this is the beginning of the interval, okay? And let's take B to be C plus some epsilon. So let's take B to be C plus epsilon. Okay, so here it's B. Now, f of A is equal to f of C is this point here. This is f of A. And this is f of B, right? Now I should choose a point C between them. So let's take C to be this point. There is no point x naught. Remember, intermediate value property says there should be a point x naught in this interval, in the blue interval. As you can see, in this interval, there is no intersection between this line and the graph of the function. It doesn't matter that it has intersection somewhere else. The property says in the interval A to B, and we can see here there is no point in this interval such that its f is equal to C. So G also doesn't have intermediate value property. If you look at the last example, of course, it is not continuous at 0. But obviously it has intermediate value property. I mean, for any 2 points we choose, well, maybe it's here actually. Any point between them we choose, there are many, many, many points where their f is equal to that number c. So sine of 1 over x is, okay, I would erase these things. So sine of 1 over x is an example of a, say from, I would define it. First of all, let me write it a little bit more carefully. Sine of 1 over x, it's a function defined on r minus 0 to r. Sine of 1 over, it's actually continuous on its domain. But if I define f of x to be sine of 1 over x when x is not equal to 0 and 0 when x is 0, this function f is not continuous. Because the limit of sine of 1 over x when x goes to 0 does not exist. Right? Therefore, this function f is not continuous. But just by looking at the graph, you can guess that it has. And then at 0, we define it to be 0. It has intermediate value property. Okay, now let's go back to Darbus theorem. Suppose we have a function f from, say, r to r, an interval to r, which is differentiable. F prime from r to r is not necessarily continuous. This function is not necessarily continuous. But although it might be discontinuous, it still has intermediate value property. I would prove it. The proof is not very hard. Let's take two numbers a and b in R. Say a is less than b. Look at f of a and f of b. Let's say also f of a is less than f of b. Other cases are similar. The other cases where f of a is equal to f of b or it's greater than f of b. Okay, so the graph of the function, graph of f prime would look like this. There is a here. We have the point A, and then we have the point B. And I want to say for any number C between f of, well, sorry, I mean f prime at A and f prime at B. For any C between f prime of A and f prime of B, we want to say there exists a point x naught such that f prime at x naught is equal to C. That's what we want to prove. Okay. Okay, so let's consider this quantity f of b minus f of a over b minus a. There is a, there is b. Look at this quantity fb minus fa over b minus a. And look at this quantity c. Now this number is either greater or equal to c, or it's equal to c or less than c. So there are different cases. It's greater than c, It's larger than C. It's equal to C. And so that's the first case, that's the second case. And the third case is when f of b minus f of a over b minus a is less than C. Now, if it's equal to C, we are, look at this case, if f of b minus f of a, b minus a equals to C, okay, it means, well, this is the graph of function f. Suppose it's graph function f. It means C is a point where the tangent line to the function at that point is equal, has the same slope as the line which connects a and f of a and b and f of b, right? That's what it means. Okay, so anyway, it's when f of b minus f of a over b minus a is greater than C, it means the function is kind of like this. This is the graph of the function which connects these two, and C is a point where the tangent looks like this. It has the less slope. Okay, we have these three cases. Let's consider one of them. Let's consider the first case. The other cases are similar. Let's just prove it in the first case. So suppose this case happens. F of b minus f of a over b minus a is larger than C. Okay. Okay, what can we do now? How can I show there exists a point x naught such that f prime of x naught equals C? Does anyone know the answer? Okay, this is a little tricky. I should define a new function. So define the new function g of x to be f of x minus f of a over x minus a. We are defining this function from interval a, b to r. Define it to be that when x is greater than a, and when x is equal to a, define this thing to be derivative at the point a, f prime at the point. Let's define this function. Remember, we were assuming we are in the case where f of b minus f of a over b minus a is larger than C. Actually, we can assume greater or equal, so we would solve the first and second case simultaneously. Okay. Now, look at g of a. So g of a is equal to, first of all, this function g of x is continuous. It's something you can verify simply. So g of a is defined to be f prime of a. And we assume C is something between f prime of a and f prime of b. So C is greater than f prime of a, right? On the other hand, look at g of b. G of b is f of b by definition minus f of a over b minus a. And we assume this number is greater or equal than C. Okay, let's say it's just greater. That would be simpler to handle. Okay, so C is something between G of B and G of A. Also, G is continuous, and any continuous function has this mean value property. So G is continuous. C is between G of A and G of B. Because G is continuous, G has intermediate value property. Therefore, there exists some x naught in the interval AB where g of x naught is equal to c. But what is g of x naught? G of x naught is f of x naught minus f of a over x naught minus a equals c. Right? Is it clear up to this point? Is there any question? So I defined a new function g, and I show, well, g is continuous, and therefore we can use intermediate value property for this new function g. Okay, so at this point we get that f of x naught minus f of a over x naught minus a equals to c. But look at this quantity here, f of x naught minus f of a over x naught minus a. If you look at the graph of the function f from a to x naught, this quantity here, f of x naught minus f of a over x naught minus a, is the slope of the graph here. Maybe draw the graph like this. This is the slope of this segment here. And mean value theorem tells us always there exists another point, say y naught or x1, y naught, here between a and x naught, such that this thing is equal to the derivative of f at y naught, right? This is the mean value theorem. Well, f of x naught minus f of a over x naught minus a equals to c. And the same thing is equals to f prime at y. Therefore, c equals to f prime at y. And that's what we were looking for. We were looking for a point y naught between a and b such that derivative there is equal to c. And we proved it. The other cases are very, very similar. So we proved, if we have a function f which is differentiable, f prime might be discontinuous, but still has intermediate value property. And that's important. Okay. Is there any question? If not, let's start integral. Okay. Okay, first question. Suppose f is a function, an integrable function, say a continuous function from the, a continuous function from 0 to 1 to 0 plus infinity. It's non-negative function. Suppose integral of f x dx from 0 to 1 is 0. Prove f is 0 everywhere. It's the function, the constant function 0. Okay. So the point is that here the range is 0 to infinity, which means f of x for any x is greater or equal than 0. We want to show actually it has to be 0 everywhere. Okay, think about that for a few minutes and then tell me your idea. Okay. Does anyone have any idea what we should do?
Could we try to prove using contradiction, maybe? So saying it's not,
Yes. Yes.
saying it's not zero somewhere, and then that the integral will not be zero.
It's continuous. So specifically, if there exists a point where it's not equal to zero, then there exists an interval around that point where it's not equal to zero.
Yeah, both of you are right. Well, if you combine what you said, that's the answer. Yeah, that's right. So, well, as you mentioned, first we are trying to prove it by contradiction. So proof by contradiction. Suppose it's not true. Well, if it's not true, it means there exists a point x naught where f of x naught is not zero, but because the range is from 0 to infinity, it has to be strictly positive. But also, remember the fact that the function f is continuous. F is continuous, right? So because f is continuous, it means f is continuous. It means if f is positive somewhere, it has to be positive like on an interval around that, right? Because f is continuous, f is like that. So if there is a point x naught where f is continuous there is an interval around that, where on that interval, f is also continuous. So there exists some epsilon, such that if you look at x naught minus epsilon and x naught plus epsilon, f is positive on the interval x naught minus epsilon and x naught plus epsilon. Okay. Now look at the integral of fx dx from 0 to 1. We can break this integral from 0 to x naught minus epsilon. Then we have an integral from x naught minus epsilon to x naught plus epsilon. And then the rest. So I'm saying the integral we can break it into 3 parts. There is an interval which we know the function is positive there, right? There is one interval before that, the red interval, and then there is the black interval where we know the function is positive, and then the rest until 1. Because the function is positive, this integral is greater or equal than 0. It might be 0, but it's not negative. This is also greater or equal than 0, right? So, well, let me erase this thing here. So this thing is greater or equal than the integral over x naught plus epsilon and x naught minus epsilon of f of x dx. But here the function is positive, right? And it's continuous. How can I say this? I want to say this quantity is a positive quantity. How can I say that? Can we approximate this value? What does it equal? What is it equal to? So we know integral of f of x dx from 0 to 1. Of course, it's greater or equal than integral of f of x dx on a very small interval around x. But on that interval, on this interval, f is positive. Okay, and then I want to say this integral is positive. So I should approximate that. Does anyone know how can we do that? How can I show this thing is strictly positive? Look at this interval. Riemann sum definition of integral. That might work, but that would be it's not going to be easy. So the property of what is important here is that this interval is closed and bounded. And closed and bounded means it's compact. Yeah, probably we can, you're right. We can also use the Riemann definition of integral. Yeah, you're right. It's what I'm doing is a little more tricky and a little faster to do right. So you're right. So this interval is compact, and we have a positive function on a compact subset. We know a continuous function on a closed bounded interval has a minimum. F has a mean on this interval. Right? It happens at some point. So let's say it happens at a point C. F of C is the mean. But it's positive because F is positive on that interval. So F of X is greater or equal than F of C because F of C is mean, but F of C itself is positive. So F of X is greater or equal than F of C. So its integral from x naught to epsilon to x naught plus epsilon is greater or equal than the integral of F of C because F of X is greater or equal than F of C. But this is constant, so it comes out of integral. It would be just integral dx. So that's integral of 1. Integral of 1 dx is just x. From x naught plus epsilon to x naught minus epsilon is going to be 2 epsilon. So the integral of f is greater or equal than F of C times 2 epsilon, but F of C is positive, 2 epsilon is positive, this is positive. So integral of F of X from 0 to 1, which we started with, is greater than 0. Therefore, it is positive. And its contradiction. We said we are assuming integral of F from 0 to 1 is 0. So it's a contradiction. So F has to be 0 everywhere. Any question here? Okay. Oh, Nick. How can we say that it is bounded again? Well, any function, so when the domain which the function is defined is closed and bounded, on a closed bounded subset, any function has minimum and maximum. That's very important property. So here we know this interval from x naught minus epsilon to x naught plus epsilon is closed interval and it is bounded. On any bounded subset, the function has max and mean. So at a very specific point, or more than one point, it's going to get its max. At some points, it's going to get its mean. And everywhere else is going to be between these two. Okay? So when I say f of x is greater or equal than f of c, I mean on this closed bounded interval, on the interval. Is it clear? Okay. Okay, let's go to the next question. Yeah, good. So let's go to the next question. We have a function f from 0 to 1 to r, say continuous or integrable. Say it's continuous. Show that, prove there exists a number c in this interval 0 to 1 such that integral of f of x times x squared from 0 to 1 dx is equal to 1 over 3 f of c. So I have a function f. I'm multiplying it by x squared. I get a new function. I'm saying the integral of this new function is equal to 1/3 f of c, where c is a point on the interval 0 to 1. Okay, think about that again for a few minutes. Does anyone have any idea? Okay, let's give you a hint. You should use intermediate value property. Because f is continuous, you can do that. What makes it slightly more complicated and challenging is that we should use intermediate value property in a question which it involves integral. We should see how we can involve integral in this theorem. Okay, one more hint. See, again, this interval 0 to 1, I'm keep on continuing that because saying that again, because it's very important. I'm just repeating that a lot. This interval is closed and bounded. Therefore, it's compact. And a function on a compact set, any continuous function on a compact set has max and mean, which means there is a point A in this interval where f of A is mean. F of A is mean. It's less than f of x for any point x in that interval. And there is another point B where f of B is the max. So f of x is less than f of B. This is quite important. This is the second part of the hint. Okay, does anyone have any idea? If not, I can write down the answer. Let me erase these for now. Okay, so f of x is between f of b and f of a. But here we have f of x times x2, so x squared, so we can multiply everything here by x squared. We get f of bx squared is less or equal than f of x squared, less or equal than f of a x squared, right? X squared is a positive number, so it doesn't change the direction of the inequality. And then we can take the integral of all of them. So integral of f of bx squared dx is less or equal than integral of f of x squared dx, less or equal than integral of f of a x squared dx. But here, f of b is a constant number, so f of b can come out of the integral. So, so this thing is equal to f of b integral from 0 to 1 x squared dx. It's less or equal than, well, integral 0 to 1 f of x squared dx, less or equal than, again, f of a is a constant number, so it comes out of integral. Okay, is it clear up to this point? Okay. So we got to this point that f of b integral of x squared dx 0 to 1. Sorry that I have to erase until when I write until the middle of the whiteboard. It's because of some of the bugs Zoom has at this point. It doesn't work very well. So it's integral of f of x squared dx less or equal than f of a integral from 0 to 1 x squared dx. But integral of x squared, we know what it is. It's integral of x squared dx is x cubed over 3. From 0 to 1 is 1 over 3 minus 0 over 3. So it's just 1 over 3. And then we are multiplying it by f of b, so I can erase these, you know, these things. So if I multiply it by f of b, it would be f of b over 3. Less or equal than integral of f of x squared dx. Also here, integral of x squared from 0 to 1 is 1 over 3, so it's f of a over 3. If I multiply everything by 3, f of b is less or equal than 3 times integral of f of x squared dx, less or equal than f of a. Now, look, I have f of a, I have the graph of f, I have a, I have b, I have f of a, I have f of b. Now I have something, let's call it c, between f of a and f of b. Well, f of a here is above f of b. So I have something between f of a and f of b. Maybe I confused where a is like max or mean, but it doesn't matter. So it shouldn't look like this. Maybe I should. At this point, at least, I'm assuming a is max, f of a is max. Maybe I wrote it the other way, but f of a is mean. So a is max, f of b is mean. The function should be something like that. And there is a value, so this is f of a, this is f of b. And there is a value c between them. What does intermediate value property tells us? What does it tell us? It tells us, yes, there should be some x naughts or there should be some x or x naught between a and b such that f of x naught is equal to c. But what is c? C is 3 integral of f of x squared dx 0 to 1. Just divide everything by 3. It means integral of f of x squared dx from 0 to 1 is equal to f of x naught over 3. That's what we were supposed to prove. We were supposed to prove integral of f of x times x squared equals to f of x naught over 3 for some x naughts. And that's it. Any question? Okay. That's how we kind of incorporate and evolve intermediate value property in a question which also involves integrals. Okay, let's go to the third question. I don't think we can get to solve it completely today, but we can continue on next Monday. But let me write down the question. Suppose we have a function f from an interval ab to r. Well, let me ask you a question. Do you know when a function has Riemann integral? A function f is integrable in the sense of Riemann? If and only if. Does anyone know what is the criterion for this thing to be correct?
If it's continuous almost everywhere?
Yes, so that is correct. That is, say, almost correct. So the set of we should say something about the set of discontinuous points of f. This set should be what you said is kind of close, but it's not exactly the theorem. This set does anyone know something about this set? About like cardinality of this set or something like that. It should be countable, yes. So for example, if a function has 1 discontinuous point or 2 of them, it's fine. If it has infinitely many, if this infinity is a countable infinity, it's fine. But if it has uncountable number of discontinuous points, we can't work out anymore. Okay, let me just write the question then. Suppose we have, actually we should prove it with the use of this theorem. Suppose we have a function f from ab to r such that at any point c, in this interval, limit of the function f of x when x goes to c exists. It doesn't mean f is continuous there. For example, c can be like this. As you can see, the function f is not continuous at c, but the limit, it does exist. So suppose we have limit at every point c, there might be a lot more actually discontinuous points then. So we want to show f is Riemann integrable. It's a very good question, actually. You can think about that using this theorem. I will solve it on Monday. Is there any other question? Is everything okay? Okay, then. If there is no more questions, we can stop the class here and we can meet on Monday. Okay, so stay happy and safe. Goodbye.